Okay, so let us continue our discussion on micro mixers. Let us first take a very simple case where we try to mix two parallel stream of liquids. Look at the example here. Here we are talking about mixing of two parallel streams. So, parallel mixing with two streams. Okay. So, as you can see, you have two streams, one stream here and one stream there. The concentration of stream 1 is the solute concentration is C0, in another one the concentration is 0. Then we can define a, depending on the mass flow rate ratio R, we can define a the interface here. So, this will be R times W and W is the total width of the channel. Okay. So, we define a interface location R, which will be proportional to the mass fraction of solute in the final mixture, which is alpha. Okay. So, alpha can be defined as M1 divided by M1 plus M2. Okay. So, this is the mass flow rate of fluid 1, mass flow rate of fluid 2. Okay. So, we define we make some assumption, we say that it is a flat microchannel. Okay. And we say the two fluids have same viscosity and density, and we say that the velocity is uniform. So, it is a uniform velocity condition. So, velocity does not change in the axial direction, and we say there is no diffusion flux in the perpendicular to the plane, no diffusion flux along perpendicular to plane direction. Okay. So, under that assumption we say that the channel is long and width is W, and we are talking about two inlets and one outlet. Okay. So, inlet 1, the solute concentration is C0, inlet 2 solute concentration is C equal to 0. Okay. So, concentration C will be 0. So, we can write down the transport equation, which is U del C over del X will be D into del square C over del X square plus del square C over del Y square, right. Now, we try to solve this equation for this geometry. Okay. So, here we have two different fluids coming in with different boundary conditions, we try to solve this equation. Okay. So, the ratio between solute to solvent, the solid to solvent ratio is equal to alpha is to 1 minus alpha, okay, where alpha is given here, the mass flow rate of solid divided by solid plus solvent, okay. So we can define non dimensional parameters. X star is x over w, y star as y over w, C star is C over C0, and we define Peclet number as U W over D. So under using these non dimensional parameter, you can write the transport equation. So the transport equation becomes Peclet number into delta C star over del x star will be equal to del square C star over del x star square plus del square C star over del y star square, okay. So this is the non dimensional equation that we are talking about, okay, which needs to be solved, okay. So to solve this equation, let us write down the boundary conditions. So the boundary condition f of y star is going to be C star, and that is going to be if x star equal to 0 and 0 less than y star less than r. So between 0 to r, the concentration C star will be equal to 1, okay. So that is what we see here. This is the non dimensional representation of the original geometry. So the interface is going to be at r, okay. So y star between 0 to r, the concentration is going to be C star, and if y star is between r to 1, then the concentration will be 0, okay. So it will be C star if x star is 0 and 0 less than sorry, in this case r less than y star less than 1, that will be equal to 0, okay. So these are the concentration boundary conditions. Now the boundary conditions of the outlet, when complete mixing will happen, then del C star over del x star at x star tending to infinity and 0 less than y star less than 1, this will be equal to 0. So that says complete mixing, okay. So there is no variation of concentration along x direction, okay. So the other boundary condition is that we are assuming impermeable channel wall, so nothing is crushing the channel wall, okay. So in that case, the concentration variation del C star over del y star at y star equal to 0 or 1 is going to be 0, right. So that is the boundary condition that we see here, del C star over del y star equal to 0 on the bottom wall as well as in the top wall, and this is the boundary condition at x equal to infinity, complete mixing boundary condition, okay. So we have boundary condition on the all 4 boundaries to solve the transport equation. So using these boundary conditions, we can find out a solution to the transport equation. So the solution can be written as, so C star as a function of x star and y star can be written as alpha. Alpha is the mass flow rate ratios of 2 fluids, which is given there, plus 2 over pi, okay, summation n equal to 1 to infinity sin alpha pi n divided by n into cos of n pi y star into, we have exponential negative of 2 n square pi square divided by Peclet number plus Peclet number square plus 4 n square pi square square root into x star. So, that is the expression for the concentration in x and y direction. Now, if you plot C star with x star and y star, this is what we would get. So, if you look at here we are plotting C star with x star and y star. So, y star is, so let us say if this is the channel, y star is in this direction and x star is in this direction. Okay. So, you can see that this is across the channel, the concentration varies from 0 for the solvent to 1 for the solute. Okay. So, this is the at some x equal to 0. Okay. So, there is a large gradient of the concentration across the middle line. Okay. Now, as we proceed along x direction, this gradient is going to reduce, and at some point, so this is where the complete mixing is occurring. So, there is no gradient along the y direction. Okay. So, what we observe from here is, so the first observation is the concentration profile, the gradient of the concentration profile decays along the flow direction. Okay. And the other thing that we observe from the equation, if Peclet number is going to be less, then the decay in the concentration, gradient of the concentration is going to happen faster. Okay. So, what it means is that for small Peclet number, it leads to faster mixing. Okay. So, we consider a case where we have two parallel fluids, they are trying to mix with each other along a channel, and we observe that the gradient of the concentration is going to be very high at the beginning of the channel, and along the direction of the flow, along the x direction, the gradient is going to reduce, and at some point the gradient along the y direction is going to be 0, that is where the complete mixing would have occurred. Okay. So, we make two important conclusions. One is that the concentration gradient of the concentration profile along y direction decays along the flow direction, and the second conclusion is that the Peclet number is less, then the mixing is going to be faster. Okay. So, with that let us move on and talk about mixing with multiple streams, how we can divide the mixing path into multiple smaller mixing paths, and as we know that the mixing diffusion time scale varies as the square of the mixing path, and as mixing path would reduce, the mixing time would also reduce. So, that would lead to faster mixing. So, what we see here is mixing with multiple streams. So, we look at mixing with multiple streams. So, here you can look at this is one fluid. So, equal width is here. Now, instead of mixing these two fluids together, what we do is we divide each stream into two parts, as in this case. So, D is divided into, this is D by 2, and this the second fluid is also divided into D by 2. Okay. So, as the mixing path length is reduced by half, the mixing performance will improve by 4 times. Okay. So, what we see here is that we know that smaller width leads to faster mixing. Okay. So, what we do is each stream divided into n substreams, and that is known as parallel lamination. Okay. That is known as parallel lamination, and in that case the Peclet number, which is U into W divided by D. So, this W is going to reduce, okay, by going for parallel lamination. So, that would give us faster mixing. Okay. So, now let us talk about sequential lamination. Let us talk about sequential lamination. So, in parallel lamination we talk about two streams which are trying to mix. So, we divide each stream into n different parts and allow these n different parts of fluid 1 to mix with n different parts in fluid 2 separately, and then bring them back together. Okay. In the sequential mixing, the two fluids will come together, and these two fluids are divided across a vertical plane, okay, across a horizontal plane, and taken separately, and the depth of each of these fluid layers are going to be increased to the original depth, so that the mixing interface area does not change. So, they will mix separately and then brought back together, as you can see here. So, this is fluid 1 and this is fluid 2, this is fluid 1, and so these two fluids are brought in contact here at this interface. Now, the mixing plane is divided across the middle plane there. Okay. So, it is divided across the middle plane, and then these two layers are taken to a separate to two different channels. Okay. So, they are divided across this plane and taken to two separate channels. Then the channel width is channel depth becomes half here, right. Now, the channel depth allowed to increase to the original depth, as in here. Okay. So, the channel depth is allowed to increase, but the fluid width has become half, and this process is continued n times. Okay. So, it have n different sequential lamination layer, and if you do that, then the mixing is going to improve. Okay. So, what we do here is we segregate joint streams into 2 channels and then rejoin them. Okay. So, if you do n splitting and rejoining with n stages of splitting and rejoining, we would get 4 to the power n minus 1 faster mixing. Okay. So, as you can see here in this plot, so this is the mixing yield and this is the number of stages per channel. As you can see here, by going for parallel lamination, which we discussed earlier, the mixing performance increases by n square time, whereas in sequential lamination it is increasing by 4 to the power n minus 1 times. Okay. So, which is going to be higher as compared to parallel lamination. Okay. So, what we conclude from here is for same device area, the sequential lamination offers faster mixing. Okay. Because the parallel lamination improves mixing at n square and sequential lamination improves 4 to the power n minus 1. But one downside of sequential lamination is that it requires 3D fluidic structures. Okay. It requires 3 dimensional channel structure or fluidic structure, and which are not quite easy to fabricate. Okay. So, even if the sequential lamination offers better performance as compared to parallel lamination, the fabrication becomes a challenge. Okay. So, with that, let us look at one example. Okay. We take one example of a micro mixture where we try to mix ethanol completely with water in a parallel micro mixture with 2 inlets. Okay. Using a Y mixture at room temperature. The flow rates of both ethanol and water are 10 microliter per minute. Okay. Each fluid has 10 microliter per minute flow rate. The Fourier number for this case is assumed to be 0.5, and the diffusion coefficient at room temperature is given as 0.84 into 10 to the minus 5 centimeter square per second, and we want to determine the required length of the mixing channel if the channel cross section is 100 into 100 micron. Okay. So, we want to determine the required mixing length given the channel cross section is 100 micron square. So, that is first we try to answer the first question, and the second is if the above mixing channel is to be redesigned with a meander shape or serpentine shape channel to save the lateral device surface. If the channel structure is to be placed inside a square area, determine the dimension of this area and also determine the number of turns. Okay. And the third point will be if the above mixture has to be redesigned with more lamination layers, in the new design the channel length should be 1 millimeter. In how many layers should each stream be separated. Okay. So, let us just first solve the first question. So, you try to find the required mixing time the required mixing time tau is given by the Fourier number into the mixing length scale square divided by d. Okay. So, this is going to be Fourier number is typically 0.5 and mixing length is 100 micron, 100 into 10 to the power minus 6 square, okay, divided by diffusion coefficient is 0.84 into 10 to the power minus 5. So, tau the time scale is going to be 5.95 second. Okay. We can find the average velocity of the mixed liquid, average velocity of mixed liquid. So, U can be written as Q water plus Q dot ethanol divided by area. So, this is 2 into 10 into 10 to the power minus 9 over 60 meter cube per second divided by area is 100 into 10 to the minus 6 square. So, we find the velocity to be, so U is found to be 33.33 into 10 to the power minus 3 meter per second. Okay. Now, we find the required length of the mixing channel. So, required length will be L will be U into tau. So, U is 33.33 into 10 to the minus 3, tau is 5.95 second. So, we get the mixing length, the length required for the mixing to occur is as 198 millimeter. Okay. So, that answers the first question, determine the required length of the mixing, which is 198 millimeter. The second question, we are trying to use a serpentine save to save the lateral device, and if the channel structure is to be placed inside a square area, determine the dimension of this area. Okay. So, in that case, here we would have a serpentine channel structure something like this, and if we say, so we make some assumption, we say that the channel width is same as the gap. Okay. So, this is where the material is and this is where the channel is. So, if this channel width is same as the gap between the channels, okay, so we make assumption that the channel walls consume same area as the channels. We can find the total surface area, the total surface area A will be 2 into W into L, which is 2 into 100 into 10 to the power minus 6. So, we are calculating in micron. So, this is 100 micron into length is 198 into 10 to the power 3 micron. So, the area is 3.96 into 10 to the power 7 micron square. Okay. So, we can find out the dimension of the square area or the side of the square area, the dimension of the square area A will be square root of A, which will be square root of 39.6 into 10 to the power 3 micron. So, that will be 6293 micron. Okay. So, A will be 6293 micron. So, each side of the square area containing the serpentine channels would have 6293 micron size. Now, if you say that each turn consumes twice the channel size, so 2 into 100 micron, okay. So, that is for the wall, and another 2 into 100 micron for channel, okay, that is quite obvious. So, each turn will start from here to the middle of this, okay. So, we will have 2 channels and 2 channel widths, okay. So, this is one channel width here and there. So, there will be 4 channel widths. So, you can find total number of turns. N will be the total size 6293 divided by 4 into 100 micron, that will be 16 turns. So, you would require 16 turns to accommodate the serpentine feature on the square area, okay. Next is the above mixture has to be redesigned with more lamination layers, and so that the channel length should be limited to 1 millimeter, okay. So, we have to find how many layers should each stream be separated. So, that for lamination we can say that tau nu is the time of mixing when you have more than one lamination, let us say n lamination layers. So, tau nu will be tau old into L nu divided by L old, okay. So, diffusion time scale is proportional to the mixing path, okay. So, you can write tau nu equal to tau old into L nu over L old. So, tau old is 5.95 seconds, L nu we want to limit it to 1 millimeter, but existing is 1898 millimeter. So, the tau nu is going to be 3 into 10 to the power minus 2 second, okay. So, if you can mix as fast as 3 into 10 to the minus 2 seconds, then the mixing required length would be 1 millimeter. Let us say we assume each layer is converted to n sub layers, okay. So, the channel width, channel mixing path will be W over n, okay. So, the new mixing time tau nu will be equal to 0.5 W square divided by n square d square, okay. So, that is equal to, so we can find n as W divided by 2 tau nu d square. So, n will be 100 into 10 to the power minus 6, that is the width of the channel, 2 into tau nu is 1 millimeter, sorry, tau nu is 3 into 10 to the power minus 2 seconds. So, 3 into 10 to the power minus 2 seconds into d is 0.84 into 10 to the power minus 9, right. So, square root of that, if you calculate n will be 14. okay. So n equal to 14. So what it says is that if you can divide each stream into 14 different parallel lamination layers, we can limit the required length for the mixing to happen, we can reduce it by 200 times. Okay. So in that case the length reduces by 200 times. Now let us look at, if instead of parallel mixing, if you go for sequential lamination. So let us say instead of parallel lamination, if you go for sequential lamination, then how many layers we would need. Okay. So in that case we can write for the parallel lamination, tau new over tau old will be 1 over n square, and sequential lamination tau new over tau old will be 1 over 4 to the power, let us say m different stages we are considering, 4 to the power m minus 1. So now for same improvement 1 over n square will be equal to 1 over 4 to the power m minus 1. So in that case we can find m equal to 1 plus 2 of ln n divided by ln 4, which will be 1 plus 2 ln 14. So 14 layers in parallel mixing divided by ln 4, so will be equal to 5. Okay. So m equal to 5. So what we saw that if instead of going for parallel lamination layers, so in which case we would require 14 different parallel lamination layers, if we go for sequential lamination layer we can do it with 5 different stages. Okay. So only 5 stages required in sequential lamination. Okay. So with that let us talk about sequential segmentation. So here we talk about sequential segmentation based mixing. Okay. So in sequential segmentation the mixing is going to happen along the direction of the flow. So we alternatively inject the solute and the solvent into a mixing channel alternatively by using valve, and we allow these blocks of solute to mix with the solvent along the direction of the flow. Okay. So that is what is shown here. If you look at here, the solute and the solvent, they are injected into this mixing channel alternatively. So we create blocks of this solute in the solvent. So the mixing is going to happen along the direction of the flow as opposed to across the channel as you have seen earlier. Okay. So now this control of the solute and solvent can be done by controlling the mixing ratio. Okay. So alpha is the mixing ratio, which is the ratio between the solute to solvent, and that can be done by controlling the valve mechanism. Okay. So let us say for alpha t by 2, okay, so the time period of the valve is t, so this is the time period is the t. Okay. So for alpha t times the solute is switched on, and for t minus alpha t divided by 2 the solvent is turned on. Okay. So if you do that, then we are interested to see how the mixing profile is going to change. Okay. So we are doing solute and solvent alternatively injected, okay, and this is using valve. Now let us consider a case where the width of the channel is greater than height, okay. This width here we are talking about is greater than the height, so we use a 1D model, okay. It is similar to flow between two parallel plates. So in that case we can write down the expression for the velocity. So for flow between infinitely long parallel plates, uy will be 6 u into 1 minus y over h into y over h, okay. And where u is the mean velocity and y is along the channel width and h is the channel width, okay. So now since we are talking about parallel plate where the width is large compared to the height, then what we are saying is that the profile is going to be parabolic across the height and it is going to be flat across the width, and this parabolic profile will lead to axial dispersion. So there is going to be axial mixing along the flow direction. So what is going to happen is we will get a flat profile along width and parabolic velocity profile along height, okay. So and this parabolic velocity profile will lead to axial dispersion, okay, for which the mixing will happen along the flow direction. So we can define a parameter called effective diffusion coefficient. Effective diffusion coefficient, and which is given as d star is d plus h square u square divided by 210 d, okay, and this is using the Taylor-Harris approach. Okay. Now if you assume that the concentration does not change across the height or in the width, okay, only it changes along the flow direction, then we can attempt to solve the transport equation analytically, okay. So we make assumption that concentration does not change with width or height, then you can solve the transport equation, which is del C over del T plus u del C over del x is equal to d star del square C over del x square, okay. So this is the transport equation that we are trying to solve here, because it is unsteady case because everything is time dependent, and so u is the flow velocity and t is the switching period, okay. So the segment length of one segment is going to be u into t, okay. So let us define the boundary conditions at inlet, so which is x equal to 0, right. So we can define C any time t at 0 equal to, it will be C0 when 0 less than t less than alpha t by 2. So because we are doing the solute injection for alpha t time, this will be C0 at alpha t by 2. So we start taking at the middle, the first t equal to 0 will be at the middle of the solute injection. So for alpha t by 2 concentration will be C0, and then when this will be 0 when alpha t by 2 less than T less than equal to T minus alpha T by 2, okay. Then it will be again C0 when T minus alpha T by 2 will be less than T less than equal to capital T. So that is how the concentration at the inlet is going to be controlled. Now we can non-dimensionalize this equation, the transport equation, using the following variables. We can use C star as C over C0 and X star as X over L and T star as T over T and Peclet number equal to UL over D star. So if you use these parameters, the transport equation will become del C star over del T star will be 1 over Peclet number minus 1 over Peclet number into del square C over del X star square. So this is VC star minus del C star over del X star, and the boundary conditions that we just outlined, these boundary conditions in the non-dimensional form will reduce to, so the boundary conditions at inlet C star T star 0 will be 1 if 0 less than T star less than alpha by 2, will be 0 if alpha less than T star less than half, and for complete mixing C star at infinity will going to be alpha, right. So we can write down the solution for this case. The solution can be written as C star X star T star is going to be the real part of alpha plus 1 to infinity 2 sine alpha pi n over pi n into exponential half Peclet number minus Peclet number square plus 8 pi n into Peclet number into I square root, okay, into, so into X star then exponential into exponential 2 pi T star into I, okay. So that is going to be the expression for the non-dimensional concentration, that is how it is going to vary with X star and T star. Now if you plot this with respect to the Peclet number along the X star, so C star if you try to plot with X star, so along the mixing length, you compare two cases, in one case Peclet number is 1, the other case Peclet number is 100, and at a low Peclet number, since the diffusion is more dominated, okay, so diffusion is more dominant, the final concentration is going to be attained pretty quickly, okay. So this is where at this X it almost reaches a steady concentration very quickly. If the Peclet number is 100, so depending on the solute and solvent concentration, the concentration is going to fluctuate along the flow direction and it takes a much longer time to reach a mixed concentration state. Similarly, if you compare two solute to solvent flow rate concentration ratios, one case alpha equal to 0.5 and the other case alpha equal to 0.25, and where we have more solute coming in as compared to the solvent, the final concentration is going to be higher as compared to a case where the solute concentration is lower. So those are two important conclusions that we make from here, okay. So let us quickly look at few more types of passive and active mixtures. So these are some of the chaotic advection micro mixtures. So, we introduce structures in the flow channel itself which would create bulk movement of the fluid that would help the mixing of two fluids. So, in this case we introduce the variations of the channel cross section along the flow direction. Also here we are introducing post on the flow channel. So, this is at high Reynolds number how the advection can come into play to improve the mixing. At low Reynolds number we can use features like depression in the channel as well as ridges and these Sebron structures in the flow channel to improve mixing. We can have active mixing where you can use external energy, as you can see that here solute and solvent are coming into a mixing channel where we define electrode patterns are present along the channel, and by controlling the voltage in this case for example we can perturb the interface so that the two fluids will talk to each other better to improve mixing, and this is what happens in active micromixtures. We can use electric field, we can use magnetic field, and we can use thermal gradient to improve mixing between two fluids. Okay. So that completes our discussion on micromixtures. So with that let us stop here.